Well, we recall the last theorem that we proved yesterday, namely that when a function is differentiable, its derivative has intermediate value property. Let us just recall that. So this is the theorem. Suppose f from AB to R is differentiable, then f prime has intermediate value property. Okay. Let us just recall that intermediate value property means if the derivative takes any two values, then it takes all the values lying in between those two values, and those values are taken actually in between those 2 points where those other values are taken. Okay. Anyway, we have explained this in detail in the last class. Now one of the corollaries of this is the one which we wanted. Okay. Again we have the same hypothesis, then f prime, okay, let us say okay, so f prime does not have any discontinuity of the first, any, let us say any jump discontinuity. Of course it can have discontinuity of the second kind, and we have seen an example of that type of function. Okay. Now how does one prove this? Of course there is basically one way of proving that. You assume that it has a jump discontinuity and arrive at a contradiction. Okay. So that is how we proceed. Okay. Suppose f prime has jump discontinuity at some point x naught in AB. What does that mean? It means that the limit of f prime as x goes to x naught exists, that is left hand limit exists, right hand limit exists, but those are different. Okay. That is the meaning of jump discontinuity. Okay. So let us say that suppose I call this left hand limit as alpha, let alpha be equal to limit f prime x as x goes to x naught from negative side, from left side, so x goes to x naught minus. Okay. And let us say beta is limit as x goes to x naught from the right hand side f prime x. Then jump discontinuity means alpha is not equal to beta, alpha is not equal, and alpha is not equal to beta means what? Either alpha is less than beta or alpha is bigger than beta. Let us take any one of the cases and give the proof in that. The proof in the other case will be similar. Okay. So this is standard terminology for this kind of thing. One says that without loss of generality assume that alpha is less than beta. Okay. That is, this is a standard way of saying it. Say that this is without loss of generality. This is the term, without loss of generality assume alpha is less than beta. Okay. Also we have to say something about the value of this f prime at the point x naught also. Okay. Value of the f prime at a point x naught, it may be alpha, it may be beta, or some totally different number. Okay. Anyway, it does not matter. So suppose f prime at x naught is equal to some, let us say, delta. Okay. Now we will choose some number which lies between alpha and beta, which lies between alpha and beta, but is different from delta. Okay. Okay. So suppose this we can always find because there are infinitely many real numbers lying between alpha and beta, so we can easily choose one which is different from delta. Okay. Choose, let us say, choose gamma such that alpha less than gamma less than beta, and gamma is also different from this f prime x naught, okay, which we had called delta. Okay, this does not matter really whether we call it delta or not. Okay. Now, if we knew that at some point f prime x is alpha f and at some point f prime x is beta, then we could have said that at some point it has to take the value of gamma, but that is something that we do not know. Okay. All that we know is that the limit of f prime x as x tends to x naught minus is alpha, but does not matter. Okay, we can use that fact that this is the limit. So we can say that suppose we consider any epsilon. See, since alpha is less than gamma, gamma is less than beta, I can always think of epsilon such that alpha plus epsilon is less than gamma, and similarly beta minus epsilon is bigger than gamma. Okay, so we can say that consider epsilon bigger than 0 such that alpha plus epsilon is less than gamma. Of course, gamma will be and less than beta, and gamma is less than beta minus epsilon. Of course, this will be bigger than alpha, this will be bigger than alpha, and this will be less than beta. Okay. And we shall use the definition of this left hand limit for this epsilon. Okay. For this epsilon, okay, there exists, let us say there exists, let me say delta 1 bigger than 0 such that if you take any x between x naught minus delta to x, if you take any x between x naught minus delta to x such that for all x in x naught minus delta to x, what should happen? F prime x should lie between alpha plus epsilon and alpha minus epsilon. Okay, for every x in x naught, that is the meaning of left hand limit, right? That is the meaning of left hand limit, right? So for every x in x naught minus delta to x, f prime x lies between alpha minus epsilon to alpha plus epsilon. Okay. Right. Similarly, we use this fact also. Since the right hand limit is beta, there will exist for the same epsilon, there will exist some delta 2. Okay, so there exists some delta 2 bigger than 0 such that for every x in, now this time, so this should be x naught to x naught because it is a right hand limit. Okay, for every x in x naught to x naught plus delta, for every x in x naught to x naught plus delta, what should happen? F prime x should belong to beta minus epsilon to beta plus epsilon. Okay. Can you see that this contradicts this intermediate value property? Okay. See what is happening here. Okay, you have this x naught in x naught minus delta to x naught plus delta, f prime x takes the value between, okay, let me draw this alpha and beta. So this is alpha, this is beta, this is gamma, and this is something like, let us say this may be alpha plus epsilon and this may be beta minus epsilon. Okay, right. In the interval x naught minus delta, oh, let us suppose this is x naught minus delta and say this is x naught plus delta. In this interval x naught minus delta to x naught, all values of f prime x lie between this alpha minus epsilon to alpha plus epsilon. Okay, f prime x naught is some value delta, okay, which is not same as gamma. Okay, and for all values in x naught to x naught plus delta, the value lies in beta minus epsilon to beta plus epsilon. Okay, that means in this interval alpha plus epsilon to beta minus epsilon, no value is taken. Okay, no value is taken. That is clear. So that clearly contradicts this intermediate value property. Okay, so that means the derivative cannot have a jump discontinuity, right. You can compare this with the properties of monotonic functions. In case of monotonic functions, we have shown that it has only jump, if at all discontinuities are jump discontinuities. All right. Okay. Now let us move forward to some other natural extensions of mean value theorems. See, all these we have seen as consequences of mean value theorems. There is a most general mean value theorem which you would have, I am sure you would have heard of, what is called Taylor's theorem. Okay. Now what is involved in Taylor's theorem? In Taylor's theorem, we basically are interested in approximating a given function by a polynomial, and a polynomial of as high degree as possible. Now what is the highest possible degree that you can go to? That depends on how many derivatives the given function f has. Okay. So let us begin with saying that suppose f has derivatives up to order n. Okay. Then let us say that suppose f has derivatives up to order n, let us say in some interval suppose I call it interval I, in some interval I containing the given point A, containing the point A. Now suppose we want to find a polynomial in such a way, suppose we want to, okay, instead of taking the order n, see usually the thing is, if we want to find a polynomial of degree n, then in order to understand the difference between that polynomial and f, that difference is given in terms of the derivative of order n plus 1. So let us assume that it is up to order n plus 1, and suppose I take the polynomial Pnx, suppose Pnx is the polynomial, and since we are interested in what is happening near A, we shall write this polynomial in terms of x minus A. Okay. And so suppose the coefficients are, let us say, C0 plus C1 into x minus A, etc., plus C2 into x minus A square, etc., going and this way. The last will be Cn into x minus A to the power n plus 1. So how do we want to choose this polynomial? We want to choose it in such a way that the values of the function and its derivatives should coincide with the values of this polynomial at each point. Okay. So that means first thing that I need is this, f of A is equal to Pn of A. Okay, f of A is equal to Pn of A. Okay. And similarly, I want, let us say, f prime A equal to Pn prime A, etc., and in general up to nth derivative of f at A, that should be same as nth derivative of Pn at the point A. Suppose I want to, that is, I want to choose a polynomial that satisfies these conditions. Okay, right? Choose a polynomial means what? Choose the coefficients. Choose the polynomial means choose the coefficients. Okay, all right. Now what we are saying is that these conditions immediately fix these coefficients C0, C1, C8. There are n plus 1 coefficients, there are n plus 1 conditions here. Okay, okay. So how does that fix? Let us look at this. What is Pn of A? Pn of A is C0, right? Pn of A is C0. So that immediately says C0 must be same as f of A. Okay, and what about okay, what about Pn prime at A? You have to differentiate this Pn prime at A. So it will be this derivative, this will be 0, C1 plus C2 2C2 into x minus A, etc. So when you put x equal to A, all the other terms will vanish. So Pn prime A, that is equal to C1. Okay, so which is same as saying that C1 is same as f prime at A. Okay. Okay, let us do for one more. If you look at Pn double prime at A, suppose I want this. Okay, then when you differentiate 2 times, this will be 2C2 into x minus a, 2C2 into x minus a, and then all the other terms will involve x minus a. So Pn double prime a, no, it will not 2C2 into it will be just 2C2, okay, it will be just 2C2, okay. So Pn prime a will be just 2C2, or which is same as saying that C2 is f prime a divided by 2, okay. Sorry, f double prime a divided by 2. In the same way, you will be able to put that C3 is f double prime a divided by 2 into 3, which is factorial 3, etc. In general, you will get these relations. Cj is equal to jth derivative of a divided by factorial j, okay. So using all this, one can say that this polynomial Pnx becomes fa plus x minus a into f prime a, etc., plus f double prime a divided by factorial 2 into x minus a whole square, etc., etc., and nth term will be nth derivative of a divided by n factorial multiplied by x minus a to the power n, okay. Okay, this is just a basically elementary calculation, just using these conditions and calculating the values of C0, but Taylor's theorem is not about that, okay. What Taylor's theorem says is that how to express the difference between fx and Pnx. Taylor's theorem says, and that difference is expressed in terms of n plus 1th derivative, and in order to express that difference we are going to use either mean value theorem or Rolle's theorem repeatedly. Now how does one do that? So suppose I want to write the difference, let us say write a difference in this way, fx is equal to, or so fx is equal to Pnx plus some term here, okay, Pnx, because we do not expect that fx will be equal to Pnx for all values of x, okay, unless f itself is a polynomial, okay, unless f itself is a polynomial of degree n. So let us write the difference as something like this will be some term. So to express the difference, in fact that will also depend on what is x, okay, the difference will also depend on what is x. So what we will do is that let us, to begin with, let us just fix some x in I, okay. What is I? I is an interval containing the given point a, okay, then fix some x, then we will choose a number such that this difference can be expressed as Pnx plus something like m into x minus a to the power n plus 1, x minus a to the power n plus 1, and then we shall say how we can find m, how we can find the value of m, okay. So let us say fix x in I, so choose m such that f of x is equal to Pnx plus m into x minus a to the power n. Of course you cannot expect that the same m will work for all x, this m will also depend on x, but now we have fixed x, so this m works for that. So we can say that m is nothing but fx minus Pnx divided by x minus a to the power n plus 1, okay, alright. Now we will do something similar that we have done in case of proof of the mean value theorems, okay. What we did there was that we constructed an auxiliary function and applied Rolle's theorem or mean value theorem to that function, okay. So now we will define auxiliary function, suppose I call that auxiliary function as f, so define f, define big F from I to R as follows, right, big F, okay. Since we already fixed x for variable, I shall use some other later, okay. So let us suppose I call big F at t, suppose that is same as Pn at t plus m into x minus, not x, I will say t minus a t minus a to the power n plus 1. Okay, all right. No, there is one more term required. Okay, f of t, because if I simply say that it will have no relation with the function small f, okay, it has to depend on small f. So f of big F of t is equal to small f of t minus this. Okay. Okay. Now what can we say about the properties of this function f? Okay, this function big F. See, after all, what does this big F depend on? It depends on small f, Pn, and this t minus a to the power n. In fact, this is also polynomial, right? So this these two are polynomials, so they will have derivatives of as many orders as you want. Okay, and this small f has derivatives of orders n plus 1. So big F also has derivatives of order n plus 1 in the interval I. So let us just take that for record. So f has derivatives of order n plus 1, that means all derivatives up to order n plus 1. Okay. One more thing, what is f of a? What is big F at a? It is small f at a, okay, small f at a minus this Pn at a minus, put t equal to a here, so that is 0. Okay, so minus 0. But what is f of a minus Pn of a? That in fact that is our starting point, both of them. Okay, so this is 0. Okay, so f of a is 0. Okay, what is f of x? You look at this. Okay, so f of x big, that is big, also big F at x is f of x minus Pnx minus m into x minus a to the power n plus 1, that is 0. That is reason for choosing m in this manner. Okay, this choice of m gives big F at x is equal to 0. Okay. Now what is the obvious thing to say after this? You have a function big F which has derivatives of sufficiently order, and it is 0 at a and x. So what follows from Rolle's theorem? That there exists some point lying between a and x. Okay, let us assume that x is bigger than a. There exists some point lying between a and x such that big F prime at that point should be 0. Okay, so suppose we call, okay, so again this big X may be either bigger than a or it may be smaller than a, but it does not matter. Okay, so again I will say that as we did earlier, let us say without loss of generality. Okay, we will use this argument again. Without loss of generality, assume a less than x. Okay, a less than x. Then there exists a point, suppose I call that point alpha 1, such that a is less than alpha 1 less than x, such that at that point f prime at alpha 1 is 0. Okay, at that point f prime at alpha 1 is 0. Okay, so you can say that by Rolle's theorem there exists alpha 1 such that a less than alpha 1 less than x and big F prime at alpha 1 is equal to 0. Okay. Okay. Now let us go once. Is this clear? So we let us say this is the interval a to x. This is the interval a to x. We have found some point alpha 1 such that at this point f prime at alpha 1 is 0. Okay. All right. Now you look at the function f prime. Okay. Look at the function f prime. Okay. So what is f prime? F of t is given there, so differentiate that. So f prime at t that is equal to small f prime at t minus Pn prime at t and minus m into n plus 1 into t minus a to the power n, okay, t minus a to the power n. Okay. What can we say about big F prime at a? Okay. Big F prime at a is same as f prime at a minus Pn prime at a, this is 0, right? Okay. But what is f prime at a minus Pn prime a? Because that is how we chose, okay, that is how we chose the polynomials to start with. So this is 0, okay. Now you look at the function big F prime at a, big F prime, it has the next, because anyway f has derivatives up to order n plus 1, so the second derivative of f exists, so that means this function is differentiable, it is 0 at a and at alpha 1, okay. So again what follows from Rolle's theorem, that is there will exist some point between a and alpha 1, suppose I call that point alpha 2, okay, suppose I call that point alpha 2 such that at that point the second derivative will be 0, okay. So we can say that again by Rolle's theorem, there exists alpha 2 such that a less than alpha 2 less than alpha 1 and f double prime at alpha 2 is equal to 0, okay. Now do you get the idea? Okay, we will proceed in this way, differentiate this once again, okay, you will get the second derivative of t, you will get the second derivative of t, that will be f double prime t minus Pn double prime t, and this will be n plus 1 into n into t minus a to the power n plus 2, and again by the similar conditions you will get that the second derivative of f at a is also 0, okay. So you will find some alpha 3 lying between a and alpha 2 such that f triple prime at alpha 3 is 0, okay, and continue in this way, okay. So continuing, how many steps we can go? Okay, continuing in this way, you can go as long as you can differentiate f, right, and this how many times you can do, that is this you can do n plus 1 times, right, this you can do n plus 1 times because it has n plus 1 derivatives. If we do that it has some more derivatives, we could have proceeded further, but we know only up to n plus 1. So continuing, what we will get, there should exist some point, okay, proceeding in this way we will call that point alpha n plus 1, okay, alpha n plus 1. So continuing, we will say that there exists alpha n such that alpha n plus 1, a less than alpha n plus 1 less than alpha n etc less than alpha 1 and that alpha 1 is less than x, okay. So all these points alpha 1 alpha n plus 1, they are all lying between, they all lie between a and x, okay. Such that what should happen, n plus 1th derivative at this alpha n plus 1 should be 0, okay. All right, but we should have some idea of what is this n plus 1 derivative, okay. We have differentiated once twice here, suppose we do it n times, sorry not n plus 1 times, okay, differentiate this n plus 1 times. So what will happen, so what is n plus 1 derivative of f at t, n plus 1 derivative of f at t, it is n plus 1 derivative of small f at t, okay, n plus 1 derivative of small f at t what is n plus 1 derivative of this polynomial p and t, is it clear that that will be 0, it is a polynomial of degree n, so its n plus 1th derivative will be 0, right, okay. What about this, it will be m into n plus 1 factorial, okay, it will be m into n plus 1 factorial, okay. So minus m into n plus 1 factorial. Okay. Okay, put it back here, put it back here. So if n plus 1 alpha n is 0, that is same as saying that this is equal to small f n plus 1 to small f at this point alpha n plus 1 minus m into n plus 1 factorial. Right, and that is same as saying that this m must be n plus 1 derivative at this point divided by n plus 1 factorial. Okay, right, this is same as saying that this means that value of m is equal to f n plus 1 at alpha n plus 1 divided by n plus 1 factorial. Okay. So what did we say that let us come back. What does Taylor's theorem say? Suppose f has derivatives of to order n plus 1 in some interval I containing a, then what did we prove? That given x, any x in that interval I, we can find a point, in this case the point alpha n plus 1, which lies between a and x, okay, such that at that point x fx is given by this polynomial plus m into x minus a to the, but this m is given by this f n plus 1 etc n plus 1. Okay, so let us say we can now write the statement precisely. So suppose f has derivatives of up to order n plus 1 in some interval I containing a, then for every x in I there exists, okay, instead of calling that point alpha n plus 1, I will simply call that point some other number, I will say, or we can simply call that point alpha. Okay, there exists alpha between a and x such that f of x is equal to Pn of x. Okay, let us write this Pn of x given by this, okay, and we can use the summation notation to write in the short form. So f of x is sigma, let us say j going from 0 to n, jth derivative at a divided by factorial j multiplied by x minus a to the power j, that is Pnx, okay, that is Pnx, right, plus n plus 1th derivative of f at alpha divided by n plus 1 factorial multiplied by x minus a to the power n plus 1. This is the statement of the theorem, right, and proof we already considered. Okay, this time we discuss the proof first and then finally give the statement, doesn't matter. Okay. By the way, now here are a few comments. First comment is, if can you see that if n equal to 1, this is basically same as mean value theorem. Okay, suppose n equal to 1, what will happen to the right hand side? Fx is equal to there will be only two terms, j equal to 0 and j equal to 1. So what are those terms? Fx is equal to fi plus okay, fi plus you can say f prime at alpha into x minus a, okay, or which is same as saying that fx minus fi divided by x minus a is equal to f prime at alpha for some alpha lying between x and a. That is just mean value theorem, So that is why Taylor's theorem can be considered as a extension of mean value theorem. One more thing, this term this term is called remainder after n terms, okay, this is called remainder after n terms, and usually denoted by okay, this is Rn plus 1 of x, okay, so Rn plus 1, that is remainder after n terms, Rn plus 1 x, and it is this, okay, it is f n plus 1 alpha divided by n plus 1 factorial multiplied by x minus a to the power n plus 1. Of course, this is just a notation, some books may be calling it Rnx also, it does not matter, okay, it is just a matter of notation. Okay. Now you can consider the situation, suppose now f has okay, we have this is what Taylor's theorem says, if f has derivatives of order n plus 1 up to order n plus 1. Now suppose f has derivatives of all orders, okay, suppose f has derivatives of all orders, then for each n you can write an expression like this, okay, and then you can say that suppose you consider an infinite series, suppose you consider infinite series of fj a by j factorial multiplied by x minus a to the power j, okay, then this what we have called polynomial p n x is nothing but what you will normally call partial sum of that series, okay, partial sum of that series, and this remainder term will express the difference between the partial sum and the value of the function, between the partial sum of the series and the value of the function. Now suppose you are able to show that for some value of x, this for a fixed value of x, this Rn plus 1 x will be a sequence, right, for each n you have a value, so this will be a sequence. So if this sequence goes to 0, if this sequence goes to 0, what does it mean? It means that for that particular x, this infinite series will converge, okay, what is that infinite series? It is this, okay, sigma j going from 0 to infinity fjx divided by factorial j and multiplied by x minus a to the power j, okay. This is what is called Taylor series of f at a, Taylor series of f at a, some books also call around a or about a and things like that, okay, but those are basically just matter of preferences of different authors, okay. Okay, so what we observed just now is that when does this series converge? When does this series converge? It converges if you can show that sequence of remainder terms goes to 0, okay. If the sequence of remainder term goes to 0, it means fx minus pnx goes to 0, which is same as saying that pnx converges to x, or which is same as saying that this is equal to fx, right, that is what is the meaning, okay. So let us just make that observation, okay, or we can write it as a corollary. If f has derivatives of all orders, okay, sometimes this is expressed by saying that f is infinitely differentiable, okay, what we have said, f has derivatives of all orders, some people have the habit of calling that f is infinitely differentiable, okay. So f has derivatives of all orders and this Rn plus 1 x tends to 0 as n tends to 0, then fx is equal to this sigma j going from 0 to infinity, this fjx by factorial j multiplied by x minus a to the power j, okay. So this is, that means the Taylor series converges to the values of the function f. Remember, this may or may not happen, okay, this may or may not happen for all functions, there are various possibilities, that is the Taylor series may or may not converge, it may converge but it may not converge to the value of the function f, all those possibilities are there, but none of those things happens if Rn plus 1 x tends to 0 as n tends to should be infinity. Now in various well known functions we can check this, in case of various well known functions we can check this. Let us just take one or two examples. One more thing, it is just a matter of notation. Here we have taken this A is called the center of the power series, and instead of if you take A is equal to 0, then the corresponding series is called Maclaurin series. If A is equal to 0, the corresponding series is called Maclaurin series. And this is what you discuss more often. Okay. So in order to see whether this happens or not for a particular function, we should take some function which has derivatives of all orders. Okay. Of course there are many such functions. If you can of course take polynomial, but in that case the whole question is trivial. Okay. In case of polynomials, what is going to happen? If the polynomial is of degree n, then this Rn plus 1x will be 0 for all x after n plus 1, and obviously the Taylor series will coincide with that given polynomial, right. So let us take something else. So okay, the simplest such function is exponential function. Take fx is equal to e power x. Then what is so simple about this function? First of all, it is differentiable any number of times, and not only that, all its derivatives are also coincide with the given function. So we know that f nx is also same as e power x for all n. Okay. So for any x, if you look at this Rn plus 1 x, what is that? It is okay. Suppose we are considering Maclaurin series. Well, suppose we take a equal to 0. Okay. So instead of this, so this will be Rn plus 1 x will be, it will be f n plus 1 alpha, f n plus 1 alpha divided by n plus 1 factorial, and multiplied by, okay, since we have taken a to be 0, we will just say x to the power n plus 1, x to the power n plus 1. Okay. Now since if fx is e power x, this f n plus 1 derivative of f at alpha is going to be e to the power alpha, right. So this is nothing but e power alpha multiplied by x to the power n plus 1 divided by n plus 1 factorial. Okay. Now out of this e power alpha is now independent of n. Okay. E power alpha is, it is not really speaking independent of n, because it will depend on n because what is that alpha? It is the one which is given by Taylor's theorem. Okay. It is not independent of n, but we can say we know that alpha lies between a and x, and in our case, for example, suppose x is bigger than 0, then suppose x is bigger than 0, then we will have 0 less than alpha, then 0 less than alpha less than x, right. Okay. Then alpha has to lie between 0 and x. Okay. And let us assume that we know that e power x is a monotonically increasing function. Okay. So e power alpha will be less than e power x. Okay. E power alpha will be less than e power x. So we can say that this is less than or equal to e power x multiplied by x to the power n plus 1 divided by n plus 1 factorial. Okay. Okay, now we can say, and this is now this is true for all n, right. It does not depend on n, this term now does not depend on n. Okay, this term, so whether this tends to 0 or not depends on whether this part x to the power n plus 1 divided by n plus 1 factorial, whether that tends to 0 or not as n goes to infinity. Okay, right. And what is the answer for that? It is a well known, it is a well known limit. So this tends to 0 as n tends to infinity. One can give several arguments for that. in fact one can say that this is an nth term of a power series which converges everywhere, okay, which we can show by ratio test, etc. Okay. But okay, I mean that is making the things more complicated. Even in a much simpler way you can show that this sequence goes to 0 as n goes to infinity, okay. So one can say that power series, the Maclaurin series for e power x converges, and because this, remember what is the series then? Series is given by this f to the power f jth derivative of x divided by factorial j multiplied by x, and since in this case jth derivative is again e power x, so we can say that what it says is that because of the we will get that fx is equal to sigma j going from, that is e, okay, in this case e power x is equal to sigma j going from 0 to infinity x to the power j divided by factorial j, okay, and this is true for all x, for all x in R, okay. All right. And so whatever we have done in case of this exponential function, in a similar way you can do for many other well known functions which has derivatives all, for example sin x, cos x, etc., etc. Okay. What is the property of sin x or cos x functions? The derivatives are again in the same form, sin x and cos x. So suppose you come up to this step, okay, this will be either cos alpha or sin alpha, okay, then we know that that has to be less than or equal to 1, okay, that has to be less than or equal to 1, and all other considerations will remain same, okay. Now so far we have discussed the derivatives of functions which are defined on some interval in the real line and take the values also in the real line, okay. That is, so far we have been talking of functions of the type f from I to R, okay, f from I to R. Now suppose I want to change this codomain, okay, suppose I want to, instead of this R, suppose I want to take the functions which takes values somewhere else, okay. So now what is the kind of structure that we can think of? Of course we can think of the functions, for example instead of real valued functions I can think of complex valued functions, or one can take the consider functions which takes the values in R2, R3, or it can be also set of all matrices, this can be some set of functions. So in general one could think of replacing this R by some other metric space, okay, but there is slight problem there, okay. You cannot take any arbitrary metric space, because suppose you want to take, say suppose we take some x in I, okay, and suppose I want to talk about the derivative of the function at this point x, okay, then you have to think of limits of elements like this, f of x plus h minus f of x divided by h, okay. Of course dividing by h is no problem, because that is, so that metric space should have this property that there should be something like x plus h, okay. Suppose x and h both are in x, there should be something like x plus h, and there should be something like 1 by h, etc., okay. If of that means, in short, there should be these operations of addition of two elements in that and multiplication by a scalar and an element in that, okay. I think by now you would have understood that what we need there is this must be at least a vector space, this must be a vector, and in addition to that vector space we have to talk of convergence, okay, we have to talk of convergence, so it should also be a metric space, okay, and it also cannot happen that you just arbitrary vector space and you are given some arbitrary metric on that, okay, that vector space and that metric should have some relationship with each other, okay, and perhaps you would have heard of what is called a norm linear space, okay. So that is what we can say, that this R can be replaced by any norm linear space X. So in particular we can think of functions which takes values in complex numbers R2, Rk, etc. We will not go into very detailed discussions of functions of those kind, but we shall see a few elementary things about this and what are the common things between the derivatives of the usual functions and those kind of functions, and what are the main differences, but that is something we shall discuss in the next class.